Swayam Prabha. Digital India. Educated India.
Let's now look at the generalization of this problem, where now I have n bit input. Okay, and once again I have the promise that this function is constant or it is balanced. Alright. So now classically, how much time does this take me to figure this out? So n bits means that the truth table is 2 to the n rows, right. So classically, if I have to figure out whether it is constant or balanced, then what will I do? So I will have to check one more than half the number of entries in the table. This is if I do it deterministically. If I do it randomly, then I can do a little bit better. Of course, there will be some probability that I still end up with roughly 2 to the n. So by the way, 1 more than half is essentially exponential, right. So that's half of 2 to the n. Now if I do a randomized algorithm, then I can analyze what will be the probability. Basically, if the function is constant, then of course I will always get constant, but if the function is balanced, then also there is some bad sequence of coin flips that will keep giving me a constant value, right. So I can analyze the probability and see, but what we will see with quantum is that once more we can manage with a single query, and this time it is going to be a lot more, it will follow the same blueprint as the warm up example we saw, but it will be more sophisticated, and we will see the quantum Fourier transform, which I have not formally defined yet, but I have given you some intuition about it. We will start seeing it with an example. Okay, so it is deliberate that I am not defining it first. I want us to see some examples, and then we will define it and see it in other places as well. Okay, so yeah, this is where we are at. I already told you this, right. So we will just make do with a single query to f, and what's my algorithm? So actually it's going to end up being, the algorithm itself is going to be almost exactly what we saw before, except it will be generalized to n bits. So instead of taking just 0 as the top qubit, I will take 0 to the n. Okay, I will apply the Hadamard gate to this joint state, and at the bottom I will just have my same old one. So the bottom part is actually exactly what we what we already saw. Okay, so this is x, this is y, this is CF, so that means I will get x and y XOR fx, right. So y XOR fx makes sense, convince yourselves, because even though the function is n bits, it takes an input of n bits, the output is still only 1 bit. Okay, so this is well defined, and I will once again do the same thing where I apply the Hadamard on the top. Yeah, so this algorithm, it's exactly the same as the previous algorithm, but generalized to n bits. But the great thing now is that it's going to give an exponential speed up over at least the deterministic classical version. Okay, so let me once again label these states psi 0, psi 1, psi 2 and psi 3, and the algorithm will also have the same measurement as the previous algorithm. I will just measure the top n qubits. Okay, so I will run this circuit and then I will measure the top n. Okay, so let's analyze this. So let's analyze this. So just for completeness, I'll write psi 0 also. So this is just 0 1. And now what is psi 1? Well, it's going to, so it's applying the Hadamard on top, so this will give me the superposition, and it's applying the Hadamard below, so this will give me minus, right. So let's write that down. So this is x over 2 to the n over 2 and minus, okay. Now I apply CF, right, I get the phase kickback. So I can now write psi 2 as summation I can get this. So far this is just it's just application of the stuff we have seen, right. Any questions about this? Okay, so now what we do is that we apply the n bit Hadamard to the top n bits. Okay, so in order to analyze what happens, we will just set up a little bit of notation. Okay, so here is a sort of small aside. So for a single bit, right, h of h of 0 is of course the plus state, right, and h of 1 is of course the minus state. Okay. I want to claim that this implies that h of x can be written as, yeah, this I claim that h of x for a bit x can just be written as the summation over all possible inputs. Here it is just one bit input, so over 0 and 1 minus 1 to the x times z. So this is just very simple, by examining you can see that this holds. Are there any questions about this? So this is just for a single bit, but what we are interested in is for n bits. So for n bits, I can write the the Hadamard over n bits as the same thing. So now this is a sum not over 0 1 but 0 1 to the n minus 1 of so minus 1 raised to, previously it was just x times z. Now I have x and z as n bit vectors. What's a natural generalization? It's the inner product. So and this is mod 2. Okay, so x z mod 2 z1 to zn over 2 to the n over 2. Okay, and this is a very important equation that we are going to use all over the place. Any questions? So let's come back to our algorithm. Okay, so remember where we were. We were at psi 2 over here, right? So we applied the phase kickback and we got a superposition of minus 1 to the fx x minus. So this minus which is hanging around will not be interesting for us anymore, but basically we got a superposition of fxx where fx is encoded in the exponent of minus 1. So in the parity, you can say, or the sign, phase, whatever. So now so now let's come back to our problem. Okay, so now remember that on this psi 2 we apply the Hadamard on the top n bits, right? So what is our psi 3 now? It's Hadamard applied on x, right? Of course this is n bits, y plus fx as we analyzed before. So this is going to be okay. So this I have just written down what we have. Okay, so we have to now open this up. So now using this equation that we developed here, right, for a single string x, if I apply the Hadamard to it, it's going to change the basis. Okay, so now let's try to develop our intuition about this transform a little bit more. So now here note that this is just a single point, okay, and this is obviously a sum over all possible inputs, right. So I take a single point and I change the basis along which I represent this value. So what I am saying is that for this single point, what is its sort of weight along all possible z's in the space, right? And the way that we have developed this, we can see that basically the weight in this linear combination is the inner product of x and z mod 2. Okay, so once again we can ignore the normalization. So we just want to say that given this point, single point x, if I apply hn to it, right, I get a linear combination over all possible points in the space, where each point is weighted by minus 1 to the inner product of my input point and whatever point is being considered. So why is this going to, or not why, but how will this play out now? So note that because of phase kickback, I already have a minus 1 to the fx, right. So now what is going to happen, you know, this h is nevertheless going to get applied to this x. Now I am anyway doing a summation outside, but that I'll just carry that along as before, right. So this is just going to sort of sit outside, and what is going to happen now is I will get another summation inside over all possible input strings, right. So this will just be again z01 to the n, okay, and now I already have minus 1 to the fx. I'll add to this the inner product of z and x, right, and I will get z minus, and my denominator will become 2 to the n, because I had a 2 to the n over 2 before, and I'll get one more when I do when I use this step, I'll get one more. So anyway, as I said, these normalization constants typically don't matter too much. What is important over here is this. So now what we are going to see is we want to finally measure, right. So this was our algorithm, right? So we now applied the Hadamard also. So we are at psi 3. Now we want to measure and get something out of it. So what we are going to see is that depending on whether f of x is constant or balanced, all its weight will either be on a fixed point or it will not be. So the point in question is the all zeros point. Okay, so let's write it down and see. So let's consider z as the all zeros point. Okay, in this case what happens, x z is obviously 0. Okay, so psi 3 becomes 2 to the minus n summation of x over x minus 1 to the fx, right, this 0 minus. Does everyone agree? I am just zoning in on one particular point. Now now you can see where this is going, I hope, right. So f is either constant or balanced. If it is constant, right, then that means that it is always 1 or always 0, right. So I am going to add and get 2 to the n or minus 2 to the n, correct, if it is constant. If it is balanced, I will get half as 1s and half as minus 1s, this whole term will go away, right. So basically what I am going to end up with is that depending on whether it is constant or balanced, right, this point has probability 0 or probability 1. So let's write that down. Okay, so in particular this term I want to write it as summation 1 minus summation 0 depending on whether fx is 0 or 1, right. So now, right, this is 0 if f is balanced and plus minus 2 to the n otherwise, right. So in case the function is constant, then basically this and this cancel and I just get 1, right. So that means that in case the function is constant, all my probability is on this single point. So when I measure, right, if I get the all zeros string, right, then certainly that is consistent with the function being constant. Now I need to argue that it cannot also be some lower probability outcome of the function being balanced. That I can argue because we just showed that if the function is balanced, then in fact this whole term dies. So the weight for the all zeros point is 0, right. So if my function is balanced, I will not get the 0 string, I will never get it, and if the function is constant, I will always get it, right. So this gives me an exponential speed up over the classical algorithm. So once again you can see that it is a rotate, compute, rotate, right, and by doing this transformation in the way that we did, we really made use of the fact that by somehow changing the basis. Okay, so I want to ignore the first rotate because I feel that is sort of something that we already have good intuition about. The first rotate just breaks up the input, it distributes the input over all possible inputs, that is fine. then we compute. Okay, now depending on the ancillary, we get some representation of f of x in the output. Okay, now here we have used the phase kickback by taking the ancillary as minus, right. So that means we encoded the f of x value in the phase minus 1 to the f of x. We could have also done x comma f of x. That could also possibly be useful in some setting. We will see examples where that is useful, but here we encoded it in this exponent, right. So now it is the final rotation which is the real magic, where the real magic happens, right, because in this final rotation what I could see is that by doing this final rotation, right, I got this, here I got this inner product of z and x also in the exponent, correct. So I already had fx in the exponent, I added to it inner product of z comma x for all possible z's, and this allowed me to use the fact that when the function is constant versus when it is balanced, right, this term, this minus 1 to the f of x plus zx, this is the term that has encoded everything for me, isn't it, because when z is 0, then I could remove the z inner product x, right, and I could just take the summation over minus 1 to the f of x, and this is now something which gives me either 1 or 0 depending on whether my function is constant or balanced, right. So I managed to encode the information about whether the function is constant or balanced in this single place, such that when I measure I get exactly what I want. Okay, so once again we have here not analyzed the running time, which for those of us who have studied algorithms before, we generally think of complexity in terms of time complexity, sometimes space complexity. Here we are really thinking of query complexity, right, how many evaluations of the function did I need, right, and right now in my mind these problems that we saw today are not immediately useful, but they are, at least I can't think of practical applications where you would want to figure this out in this query, how many queries here or there, but it shows it starts to develop our understanding about what quantum can do, right. So here I have been trying to weave this into this story of rotate, compute, rotate, where I am hoping that we will be able to see that this rotation in addition to probabilistic computation is sort of the one extra power that quantum really has, so far as we know right now. Okay, so the algorithms that do succumb to this extra power are very naturally, in fact, cryptography algorithms, or the hard problems or the number theoretic problems that lie at the base of cryptography. And let me once again try to tell you why I think this is true. It's because for cryptography, which we will see, soon after we see a few examples of this, we will switch tracks to cryptography and we will see how some of these hard problems are used to build cryptography, and then we will come back and see how this will break that. Okay, so in cryptography, let me see if I have another scratch pad here. Good. So in cryptography, what happens is that so I want to build a kind of encryption mechanism. So there should be some encrypt algorithm and some decrypt algorithm, and there should be some way to develop like a public key and a secret key such that the two are mathematically related, so that here when I encrypt the message using the public key I get some ciphertext, and when I decrypt that ciphertext using the secret key I get the message, right. And the secrecy requirement in this example is that you know, if I have some adversary okay so if I have some adversary here who's intercepted CT, okay, this adversary should not be able to learn M, and not only should this adversary not be able to learn M, but should not even be able to distinguish between CT of M0 and CT of M1 with probability noticeably better than half. So, I won't write that right now, with probability let us say somehow better than half. So, the adversary can always win, you know, like I am going to think, or in computer science we think of the adversary as playing a game with the challenger, okay. So, when I want to argue the security of an encryption scheme, what I want to say is that, you know, the adversary is given a ciphertext of some M0 or the ciphertext of some M1. The adversary knows M0, it knows M1, and it knows the ciphertext. It merely has to map the ciphertext to either M0 or M1. So, it can always do that with probability half just by guessing, right. So, if it can do it with probability even slightly better than half, where slightly is something we can rigorously define, we will not do at this moment. If it can do it with probability slightly better than a half, then we say that it wins the game, okay. And how do we argue that this scheme is secure? How do we argue that it cannot win with probability much better than half or even slightly better than half? We do a reduction. So, this is something which I showed you in the very first class, right. I do not know if you remember. So, what we do is we build a proof. So, we build some algorithm R, okay. This takes as an instance some hard problem. So, let us say, you know, it is taken some n which is 500 bits, okay, and it is talking to another player here which we call a challenger, and what the challenger wants is factors of n, okay. So, what this reduction does is that, let me say that this adversary is called A. What the reduction does is that it will take this factoring problem and convert it into an instance of the crypto system that the adversary can break. So, let me call this crypto system as pi. So, what does it do? It converts this factoring problem into an instance of pi such that if the adversary can distinguish between CTM0 and CTM1, then the reduction can take that answer and use it to somehow factor n. So, there is a lot that will go on in this, right, but at a very high level this is what will happen. So, now this puts the following kind of burden on the hard problem on which crypto is based, okay. So, here what I showed you is that the hard problem is factoring, right. I just used that as an example. What all is needed from factoring? One is that however I embed this factoring problem into my ciphertexts, right, the ciphertext should be indistinguishable from each other, okay. So, there is some kind of one-wayness about this underlying problem, so that CTM0 and CTM1, these are not distinguishable. I cannot no adversary can look at CT_M0 and CT_M1 and tell which is which. At the same time, I want the ability to decrypt. So you see that cryptography is always standing on the slightly shaky ground, or walking this tightrope between structure and hardness. I need structure so that it decrypts, the functionality works. I need hardness so that without whatever is the secret, here the secret key, without the secret, the view appears random to the adversary. So that is why cryptography always ends up relying on problems that have some kind of structure but are assumed to have a certain kind of hardness. Okay, and coming back now to our quantum approach, what is happening is that this extra power that the quantum algorithm gave you of doing this Fourier transform in addition to probabilistic computing, this is allowing you to detect certain types of structure, right, which is inherent in cryptography. Now note that this does not mean that any type of structure can be detected. So in fact, quite emphatically no, right. Of course, these are all emerging areas of research, so we still do not know. So maybe even the problems that we currently believe are quantum hard, maybe even they will succumb to some kind of quantum attack. But so far as we know today, the extra power that quantum computing gives you does help you to sort of break a certain type of structure, but it does not help you to break certain other types of structure from which we can still get cryptography. Okay, so we will stop here. Are there any questions?